Hi everyone, I am Sudipto from the University of Virginia, and today I am going to present our paper titled AdaInf, Data-Driven Adaptive Scheduling for Accurate and SLO Guaranteed Multiple Model Inference Serving at Edge Servers. So the deep learning applications are so pervasive now. The deep learning models are used to identify the type of the vehicles and to identify the person activities in a video surveillance application. They are also used for the real-time analysis of the drone footages, for human pose estimation in virtual reality, for 360-degree understanding in self-driving cars, and in the recently popular generative AI application that can generate image or text based on the user prompt. So one significant characteristic of these applications is that most of them are multimodal applications. That means that multiple deep learning models are included in one application. For example, in the video surveillance application, given in an input video frame, the object detection model first detects the objects of interest that are the vehicles and person in this example. And then for each detected object, if it is a vehicle, it goes to the vehicle type recognition model to output cars or trucks. And if it is a person, then it goes to the person activity recognition model to output walking in this example. So the overall workflow of such an application can be represented by a directed acyclic graph or DAG. So compared to the single model applications, the multi-model applications have higher resource demand, and also there is dependency between the models uh, as illustrated by the DAG that we need to satisfy during its execution. Now, after the deep learning models are trained, the application is deployed at an edge server that serves the inference requests generated in a specific locality. There are various commercial options available now for public edge servers, for example, the Azure Stack Edge or the AWS Wavelength. To illustrate this, when an application developer develops some application, the application is deployed at an edge server, and then during inference, the user request is sent to the edge server through 5G cellular network, and the edge server responds to the user with the inference result. Now, with each inference request, there is a constraint on the inference latency. So the user might say that they want to receive the result within 100 milliseconds, which is called the latency service level objective or latency SLO. So unlike the distant cloud, the edge servers can provide millisecond level low latency services as they are closer to where the user data is generated. Now, an edge server has limited number of GPUs or low capacity GPUs. For this, the models deployed there are usually the compressed models. However, these models suffer decreasing accuracy due to data drift. For example, in the video surveillance application, at a certain timestamp in a video frame, most of the cars are personal cars. However, after a short interval, most of the cars are police cars and ambulances due to an accident. So the input data distribution has changed. And in our paper, based on real-world trace data analysis, we have shown that such data drift significantly affects the inference accuracy. To solve this, the system called AKIA proposes performing continual learning or retraining of the models at the same edge server where the inference is being executed, because performing the retraining on distant cloud delays the deployment of the updated model back to the edge server due to the edge server to cloud communication time. However, we have found that when we execute both the retraining and inference at the same edge server, there is resource competition between these two types of tasks, and this negatively affects the inference accuracy and latency. So let's look at why this occurs. So when we perform both the retraining and inference at the same edge server, the inference requests that are initiated before the completion of the whole retraining, which is 40 seconds in this figure, cannot use the updated retrained model. So these inference requests incur low accuracy. So to solve this, we can allocate more GPU resource to retraining to make the retraining faster. However, it takes away resource from inference, and as a result, the inference latency SLO violation increases. Also, the existing method traverses possible resource allocation solutions for multiple retraining and inference tasks of a DAG, which increases the inference latency and in turn the latency SLO violation. So to solve these problems, we propose AdaInf. Our goal here is to maximize the average latency SLO fulfillment and average accuracy of all the applications deployed at an edge server with short scheduling time. And we want our system to be cost or resource efficient because GPU execution is expensive. So overall, our system has three major components. The first one is the data drift aware retraining inference DAC generation. The second one is the data drift aware GPU space and time allocation. And the third one is the host memory to GPU memory communication minimization. So let's look at the first component on retraining inference DAC generation. So we observe from real-world trace data analysis that not all models of an application are impacted by data drift, and different models of an application are impacted differently by the data drift. Based on this, we produce a retraining inference DAC from the default DAC of an application. So each node of this DAC is either a retraining task or an inference task. And if it is a retraining task, we also estimate the impact degree, and the models with higher impact degree require higher retraining time with more retraining samples. Then in the second component on GPU space and time allocation, we propose a method called incremental retraining that retrains a model as much as possible before every time it is used by an inference task. So if the SLO is 400 millisecond and the inference requires 200 millisecond, we can do the retraining for the first 200 millisecond and still satisfy the latency SLO. This way, the inference requests that are initiated before the completion of the whole retraining can be executed on a version of the model that has been retrained to some extent. We observe that such incremental retraining can improve accuracy, and we also observe that if we use early exit structures of the models with incremental retraining, it can significantly improve accuracy, because when we use early exit structure of a model, we reduce the inference latency. This way, we leave more time for incremental retraining. So overall, in our allocation method, we first split the total GPU space among the applications so that their latency SLOs are fulfilled. Then, for each application, we split the GPU time to retraining and inference, considering incremental retraining. Then, we further split the GPU time allocated for the application's retraining among the multiple retraining tasks of the application based on their impact degrees. And finally, for each retraining task, we find the optimal number of retraining samples. And for each inference task, we find the optimal inference request batch size and optimal early exit structure. We also observe that when we conduct both the retraining and inference at the same edge server, the data communication time between host memory and GPU memory constitutes significant portion of the overall inference latency. So to reduce this communication time, we propose two strategies. Our first strategy is the coordination between the inference requests in a batch to maximize the usage of the GPU memory contents that are currently present in the memory. And our second strategy proposes performing priority-based eviction of the GPU memory contents that prioritizes the memory contents that will be reused sooner to remain in the GPU memory. We perform large-scale experiment using real-world applications on real-world trace data. We compare with AKIA and two variants of Scrooge, which is a cost and latency SLO efficient inference serving system. We observe that AdaInf achieves up to 21% higher accuracy. It achieves up to 54% lower latency SLO violation, and achieving the similar level of accuracy as AdaInf requires 4 times higher number of GPUs for AKIA, which means that AdaInf achieves 4 times higher cost or resource efficiency. That's all for the presentation. Thank you, and questions are welcome. I am looking for internship opportunities. Feel free to reach me at my email.